Okay, in this video, we are going to look at the definition of block codes, and we're going to see a few examples of common block codes and some performance bounds of block codes. So this is the very formal definition of a block code. A block code is nothing else as a set, and it's essentially a set of vectors of length n. So formally, we can state that the block code C, it's of length n and it's of cardinality m, and usually we choose m to be equal to 2 power k. And the block code is defined over a field, and in our case we use the binary field f2. It's a collection of m elements from f to the power n. So in our case, it's a collection of m binary vectors of length n. This is the definition of a block code. So that's essentially a code. The different x, so the different elements, they are called code words. And the length n is the block length or the dimension of the code. And as I just mentioned, usually we choose m to be equal to 2 power k, and k is the information length of the code. And we do this because we have k bits at the input. There are 2 power k possibilities of choosing this input. So by doing so, we have these 2 power k possibilities, and we can assign to each of the 2 power k different input patterns, we can assign a code word. That's what the encoder is doing. So in k is the so-called information length of the code. So very first example is the code that's given here, and we call this the repetition code. It has 2 code words, m equals 2, so that means k is equal to 1, and n is equal to 3. The dimension of the code is equal to 3, and we have 2 code words. First code word is 0, 0, 0, and the second code word is 1, 1, 1. And we see that the code words repeat. That's why it's called repetition code. So the first 0 is repeated 2 times. So overall we have 3 elements. And in the second code word, the first one is repeated 2 more times. And that's what we call a triple repetition code. So that's the basic definition of a code. And with this, we can define the rate of the code. So we already saw the rate, so we can quickly skim over it. So we saw that the rate of the code is k over n. Well, we know that m is equal to 2 power k. So we can also express it in terms of m. And in a very general way, the rate is defined as log 2 of m. And in particular, we have, for binary case, k over n. So, and we can essentially, this is something we can forget, because that's a copy-paste issue that's no longer correct. So the rate of the code is 2 power k over n, and the rate of the code is a measure of the bandwidth efficiency or the efficiency, the coding efficiency. If we go back to the example that we just saw, we have the rate of the code, which is log 2 of 2, 1, k is equal to 1, over 3. So it's 1/3. So only 1/3 of the bits in our code word are actually information bits. The rest is parity. So we have a very low rate of the code, and we transmit a lot of parity bits. In classical coding, the Hamming weight and the Hamming distance are 2 very important measures. And still, these measures persist in modern coding, as we're going to see at the end of this chapter. So what is the Hamming distance and the Hamming weight? So we have two code words, U, or they don't even need to be code words. We can define in a very general way. We have two n-dimensional vectors U and V. And we have the Hamming weight of a word U, of a vector U, which we denote by W of U, essentially corresponds to the number of non-zero symbols or bits in U. So we just count how many of the values in U are not equal to 0, and that's the Hamming weight. So for this vector, we have two non-zero weights or symbols, so the Hamming weight is equal to 2. Then we can also define the Hamming distance. So the Hamming distance is a distance measure between two pairs, U and V, and it's denoted by distance between U and V. And essentially, it's the number of positions where U and V are different from each other. So for instance, if we have the distance between 1, 0, 1, 0, 0 and 1, 0, 0, 1, 0, then we can take a look. So in the first position, both are equal. In the second position, both are equal. In the third position, we see a difference. So there is a difference in the third position. There's also a difference in the fourth position. And in the final position, both are equal again. So we see when we count in two positions, the two words are different from each other, so the Hamming distance is equal to 2. So we can express the distance in terms of the weight, because it's just, if we take the difference between those two vectors, we calculate the difference between U and V. We know we operate on a field, so we can actually calculate a proper difference. In binary numbers, minus is equal to plus. So what we can do is we can replace this minus by a plus. And then it's the Hamming distance between U plus V and 0. So we essentially what we do is we add the two vectors, the two binary vectors, and we compare how many bits or symbols are different from 0. And this is equal to the weight between U minus V. Again, if we operate in binary, it's the same as U plus V. So we add the two vectors, and it's the weight between of the addition or the sum of those two vectors. So we can do this. This is equal to the weight of the sum. So first position 1 plus 1 is equal to 0. Second position 0 plus 0 is equal to 0. Third position 1 plus 0 is equal to 1. Fourth position 0 plus 1 is equal to 1. And fifth position 0 plus 0 is equal to 0. So that's the distance corresponding to the weight of the sum of those two vectors. So the Hamming distance is actually a proper distance. It fulfills all the properties of a distance. In particular, it fulfills the triangle inequality. We're going to see in the tutorial session how you can prove this. And it was used to define the most important quantity in classical coding, which you may know already, and which is the minimum distance. So the minimum distance of a code C is the minimum of the Hamming distance between U and V, where we calculate this Hamming distance for all code words U, for all combinations of code words U and V, such that U is different from V. So we take all possible code words for U, we take all possible code words for V, we do all the combinations. So essentially we can also say that U, V are element of C squared, and U should be different from V. And then we calculate the minimum of this distance. And this minimum Hamming distance can be used to compute error correcting capabilities of a code, and most importantly for the binary symmetric channel, which was used a lot in classical coding. But it will also be important for other channels, as we will see later. So you may know these expressions. So if we have a transmission over the binary symmetric channel, then a code that has a minimum Hamming distance of D can detect all possible error patterns with D min or D minus 1 errors. So if the Hamming distance is D min, then we can detect all error patterns with D min minus 1 or less errors. And if you have a transmission over the B.Sc, then a block code with a minimum Hamming distance of D min can correct all possible error patterns with D min minus 1 divided by 2 or less errors. And these parentheses are the Gaussian parentheses. So it means that this is the largest integer that is smaller or equal than tau. Essentially it means rounding down. So taking the floor operation. That's if you have a background in MATLAB, this means floor operation. Essentially it's the largest integer that is smaller or equal than tau. So we can look at a few examples. If D min is equal to 3, that means E is equal to 3 minus 1 divided by 2, which is equal to 1. That's easy. If the minimum distance is equal to 4, that means that E is equal to 4 minus 1 divided by 2. So this is 3 over 2. And we apply the Gaussian parentheses. And this means 1.5. So we take the floor operation, and this is also equal to 1. So we can correct one error if the minimum distance is equal to 4. The minimum distance is equal to 5. That means E is equal to 5 minus 1 divided by 2. And this is equal to 2. And so on. So essentially, the minimum distance minus 1 divided by 2 is the number of errors that you can correct if the transmission happens over a binary symmetric channel. If we have a binary erasure channel, situation gets a little bit easier. So we saw already the binary erasure channel is a very good model for packet transmission over the internet. And in this case, if we have a binary erasure channel, the code that has a minimum distance of D min can correct all erasure patterns with D min minus 1 or less erasures. And it makes sense because in the erasure channel, we already know at what positions the issue is. If there is an erasure, we know we need to find the value. If there is an error, we first need to find the position where the error happened. And then we need to flip this position. Finding the position is more difficult than finding just the value of 0 and 1. So in the binary erasure channel, we have some extra information already. That's why it's an easier channel. So what happens in the binary input AWGN channel? Well, we may ask, is this still the right measure? And essentially in classical coding, everything evolved around the binary symmetric channel, because that was the dominant channel in the 1960s, in the 1970s, and even in the 1980s, because we didn't have efficient analog to digital converters, and we just used a binary thresholding device. So if the voltage is above a certain level, we put a 1, it's below a certain level, we put a 0. we didn't have a way to measure the output of the channel until the 90s, 2000s. And that was when the binary input AWGN channel became dominant, in practice at least. In research, it was dominant already earlier. And it turns out that codes that have a large minimum distance are not necessarily among the best performing codes of the binary input AWGN channel. And there is something more that is important. In particular, the turbo codes, which were the best in the 90s, were the best codes over the binary input AWGN channel. They have a very, very small minimum distance, but they have other properties that make them outstanding over this binary input AWGN channel. Okay, so now we're going to take a look at repetition codes in particular. And we already saw the repetition code. And in the general definition, the repetition code is a code that has two code words. And the first code word contains only zeros. And the second code word contains only one. So we only have two code words. We can easily compute the minimum distance. We just need to compare these two code words. And we see that they are different in every position. So what this means is that the minimum distance of the repetition code is equal to n. We saw the repetition code of length 3, and we saw that it has two code words, 000, 111. It has minimum distance of 3. So it means we can correct one error on the binary symmetric channel. We can detect two errors on the binary symmetric channel, or on the binary erasure channel, we can correct d-min -1 erasures. This makes sense. So these are equal in the case of the repetition code. If we have two erasures, it means we have at least one, or we have exactly one bit that has been received correctly. And we know this bit is either 0 or 1. If we receive a 0, we know that the other two bits must also be equal to 0. If we receive a 1, we know that the other two bits must also be equal to 1. So that makes intuitively sense that we can correct d-min -1 erasures on the binary erasure channel. And essentially it means that this is equal to n-1 erasures. So we just need one bit that we receive from the repetition code on the erasure channel, and everything else follows from this one bit. So we can represent the binary erasure channel, can represent the repetition code in as a subspace of the space of all possible code words. So we have a minimum distance of 3. So need to make a little bit of space. I didn't prepare my slides properly, as I see, but that's not an issue. So these are all the possible 8 code words, and we can nicely represent them in this as a cube in a 3-dimensional space. So every position in the code word corresponds to one coordinate. The x coordinate, the y coordinate, and the z coordinate. So for instance, this coordinate corresponds to the third bit. So let's say that this is equal to x3. This coordinate is equal to x2, and this coordinate is equal to x1. So we have this cube, and we see that the two code words are on opposite corners of this cube. And whenever we want to move from one code word to the other, we need to pass 3 vertices of this cube. So there is no direct connection. And that means that we see that because we need to pass 3 vertices, whenever we make one error, so going along one vertex means we make one error, we are still 2 more vertices apart from the next code word. So in this case, we just need to go back to the vertex we came from, and we have detected the error. And if we make 2 errors, we will always end up in a vertex that is not a code word. So also having 2 errors will always be detected because we will never end up in a code word. So that's the subspace representation of the repetition code. With this, we can define something called the hemispheres. The hemispheres is essentially a ball that we put around the code word. So we say we have a point X, which is an n-dimensional point. And the sphere of radius t, which we call a t-sphere, is the set of all points where the Hamming distance to the center of the sphere X is less than or equal to t. So formally, it's a set of all n-dimensional vectors such that the Hamming distance between A and X is smaller or equal than t. So if we have a t-sphere centered around X, this is the set of n-dimensional points that are obtained by flipping less than or equal to t bits. That's how you can also see it. So we have a vector, and we flip some of the positions of this vector. And if we flip less than t, then we are in this sphere. So what it means that if a code can correct e errors, then we put a sphere of radius e among each code word, and this will contain all the words that will get corrected to X. So not code words, but it will correct all the words, contains all the words that will be corrected to X, the sphere. So we can calculate the number of points in the sphere. So the number of points is given by this expression. So that's n choose 0 plus n choose 1 plus n choose 2, and so on. So this is equal to 1 plus n choose 2, and so on. So this 1, that is the point itself. So that's the center of the sphere. We need to count the center itself. That's the point you obtain by flipping 0 positions. Then we have n possibilities of flipping 1 position. We can flip the first, we can flip the second, the third, the fourth, the fifth, and so on. So the total number of such position is equal to n. Then the number of possibilities to flip 2 positions. So we choose 2 bits, and the possibilities of flipping those 2 is given by n choose 2. And so on. And then we just count, we sum up all those points, and that's the number of points in the sphere. And with this, we can, first we can visualize it. So here is for the repetition code, we have our subspace representation as a cube. And we put 2 spheres around the code words. And this is my attempt to draw the sphere. So this is the sphere of radius 1. So these are 1 spheres that we put around both code words. So all the points that we obtain by flipping 1 bit. So we have the point itself, this point, and this point. We have this point, all the words that we obtain by flipping 1 bit. It's this one, and this one. So we can count the number of points. So each one sphere contains exactly 4 points. And we see that the spheres are non-overlapping. So it means that we can assign the points in a sphere and correct them to our center. And both spheres cover the complete space of points. We have a total number of 8 points. We have 2 spheres with 4 points. And both spheres cover the whole space. And this is what we say it achieves the Hamming bound. What is the Hamming bound? The Hamming bound is the following. So with this sphere representation, we can get a very natural bound on the size of a code. So if we have a code that can correct E errors, and E is minimum distance minus 1 divided by 2 Gaussian parentheses, then we say that all the E spheres, they must contain distinct points. They must not overlap, because otherwise we wouldn't know to which sphere the code belongs, and we may correct it to the one center or to the other centers. So it's becoming ambiguous. To have an unambiguous situation, the spheres must not overlap. So we have a total number of M code words, and the spheres, they must be smaller or equal than the total number of points. So we take each code word. Around each code word, we put a sphere. The spheres, they must be non-overlapping. So we count. We have M code words, and each sphere contains this amount of points. So from 0 to the radius of the sphere, which is E, that's E, of n choose I. Now, what is the total budget of points that we have? We have vectors of dimension n, so there are only 2 to the power n possible points in the space. So this must be smaller or equal than 2 power n because the points are not overlapping. And then we just rearrange this expression. We put the m on the other side and say this is equal to 2 power n minus k. And we can use this bound to get a lower bound on the minimum size of a code. And that's the so-called Hamming bound. So how do we obtain the Hamming bound? Well, we just evaluate this expression. So we know that this inequality must hold. Unfortunately, this is nothing that we can solve for n, because this is an expression with binomial coefficients that contain n. This is 2 power n, but there is no way that we can rearrange this expression and solve it for n. So we need to do this numerically. And we can do this. So let's see how we do this. So first, we're looking at a specific example, a code of rate 1/2. So n is equal to 2 times k. So then we can evaluate 2 to the power n minus k. We know that 2 power n minus k is equal to 2 power 2k minus k, so it's equal to 2 power k, equal to 2 power n divided by 2. So for instance, if n is equal to 20, this would be equal to 2 to the power 10, so 1024. So we are here at 10 to the power 3, so 1024. So this is the red curve. The red curve defines 2 to the power n minus k. And notice that we have a logarithmic scale on the y-axis. And then we plot the number of points. So the sum from 0 to e of n choose I. So we do this for different values of the minimum distance. So for the minimum distance of 3, this would be equal to n choose 0 plus n choose 1, because e is equal to 1. This is equal to n choose 0 plus n choose 1 plus n choose 2. This is equal to n choose 0 plus n choose 1 plus n choose 2 plus n choose 3, and so on. So every time we increase the minimum distance by 2, we can correct an additional error, and the sphere grows by 1 in radius. And we know that this guy must be smaller or equal than 2 to the power n minus k. So obviously, this is not the case here in the beginning. There, the expressions are larger than 2 power n minus k. So for d min equals 3, we need to be here. So we need to have an n that is at least larger than 5 point something, or 6. So for be here at 6. So then for d min of 5, if we want to correct 2 errors, n should be larger than, this is roughly 13. Then for minimum distance of 7, n should be larger than 23. For minimum distance of 9, n should be larger than 30. And we can see how it grows. So now we can take those points that we calculated here, and we can plot those points. And that's what we get on the next graph. So we can plot those points as a function of the minimum distance. And that's what we get on the next slide. So that's this curve. For rate equals 1/2. That's the minimum required code word length as a function of the number of correctable errors e. And we see it grows rather steadily. And if we want to have a code that can correct 50 errors with rate 1/2, we need to have a length of our code of at least 430 something. So that's this point over here. So 430 and something is what we can correct at least. If we want to have a larger rate, then obviously this increases quite dramatically. So if we want to correct 15 errors with a rate 5 or 6 code, we need a code of length 600 at least. And this makes sense because we have a higher rate, means we have less bits at our disposal, and we can correct also less bits. So less parity bits at our disposal, so we can correct less errors than with a lower rate. Okay, that's the Hamming bound. Next, we're going to look at a very simple bound, which is less tight than the Hamming bounds for our application, meaning for binary codes. And this is the so-called singleton bound. The Hamming bound actually is a tight bound. So it means there exist codes where the Hamming bound that achieve the Hamming bound. And these are so-called Hamming codes. But other examples are Golay codes, which are not part of this course, but part of the next semester course. It is difficult to compute, though, the Hamming bound. So a bound that is simpler to compute is the so-called singleton bound. That's essentially one that is very simple to compute. It's almost trivial. For codes that are not working over the binary numbers, it is also better than the Hamming bound, at least in some special cases. But it has the advantage that it's very, very simple to compute. We don't need to mess around with binomial coefficients. We can actually solve it directly, and that's The proof is also one-liner. So how can we compute it? Well, let's take a look. Essentially, the singleton bound says that the minimum distance of a code of length n and 2 power k code words, or k information bits, is upper bounded by n minus k plus 1. Okay, that seems to be very simple. And how can we prove this? So first we say L is equal to k minus 1. So we have 2 power k code words. And now what we do is we write down the code words below each other. And we're looking at the first L positions. So for instance, assume we have a code with k is equal to 3. And L in this case is equal to 3 minus 1 is equal to 2. So 2 to the power L is equal to 4, and that's definitely smaller than M, which is in this case 2 power k, 8. So now if we're looking at the code words, and we want the code words to be distinct in the first L positions. So we write down the code words, and we're looking at the first L positions. And then we have some more values which we don't bother. So we want them to be distinct, the first L positions. So now we have 4 code words, and now it doesn't work anymore. Now we need to choose a code word that in the first L positions has a value that has already been used. So for instance, we need, let's start over, 0, 0 again. This is the so-called pigeonhole principles. So the pigeonhole principle says that we have 4 holes where the pigeons can fly into, and each pigeon wants to stay in its own hole. After 4 pigeons have flown in their holes or in the nests, there is no hole left. The 5th pigeon needs to fly into a hole where there is already a pigeon. So this is the 5th pigeon, and it needs to fly into a hole where there's already a pigeon, which is this code word. So it means that we have at least 2 code words, this one and this one. There can be more because we need to write down a few more, but we have at least 2 code words that agree on the first L coordinates. So they are the same on the first N coordinates, and they can be different on the remaining coordinates. But that means that the minimum distance must be smaller or equal than n minus L, because they agree on the first L positions. There are only n minus L positions left, so they can be different in the remaining n minus L positions, and therefore the minimum distance will be smaller or equal than n minus L. And L is equal to k minus 1, so this is equal to n minus k plus 1, and we have proved it. So the singleton bound is easy, but it's not very powerful. So let's take a look at comparing the 2 bounds. We do this first here. So this is the singleton bound for binary codes. So here we're looking at the number of correctable errors again, minimum distance minus 1 divided by 2, and the minimum required code word length. So the singleton bound says that if we want to correct 20 errors, again, we are at a rate of 1/2, means that for 20 errors, the code must be at least 90 bits long. So the admissible region is somewhere here. That's where the singleton bound says that we could possibly find valid codes. Now if we're looking at the Hamming bound, this is the Hamming bound for binary codes. The Hamming bound says no, it should be here. I'm giving you a much better bound if you want to correct, what did we say, 20 errors, around 90. The Hamming bound says, look, if you want to correct 20 errors, you better use 180 something bits at least. Because with 90 bits, you will never get there. So it's actually off by a factor of more than 2. And here you can see factor of more than 2 between the two bounds. So the singleton bound is not tight. The Hamming bound is tight, so we can actually find some of the codes that actually lie on this Hamming lower bound. The singleton bound is not tight. Singleton bound is tight only in some special cases. So what are these special cases? Special cases are when we have a so-called maximum distance separable or MDS code. So this means it's abbreviated as MDS. So an MDS code is a code where the minimum distance is exactly equal to n minus k plus 1. It's a very good code because it can detect n minus k errors, can correct n minus k divided by 2 errors on the B.Sc, and on the erasure channel it can correct all erasure patterns of exactly size n minus k. So unfortunately, you can show that the only binary codes that are actually MDS codes are trivial codes. The code that only has one code word, you cannot really use this for communicating because you will always send the same code word, so there's no information embedded. This means that k is equal to 0 because 2 power 0 is equal to 1 code word. Then the code that has a single parity bit that has a minimum distance of 2. That one is the so-called single parity-check code. That's actually a very useful code, but it cannot correct an error. So it has a single parity bit. It ensures that the parity is even, but it cannot correct errors. And then the code that has all 2 power n code words. So all the words that exist are actually code words. It's also not a very useful code because this one has a minimum distance of 1. So no detection, no correction possible. If we move away from the binary code, so if we allow the different positions to be non-binary, then we actually have MDS codes. This is the so-called Reed-Solomon codes. This is also something we're going to see in the CCAM lecture in the summertime. Okay, so we have seen the singleton bound is not very powerful. It's much less powerful than the Hamming lower bound, but it is very simple to calculate with. And in some cases, we can use it to get very good results if you want to calculate, for instance, error correcting probabilities or error correcting upper bounds, which we will see later in this chapter. Okay, with this, we have wrapped up our very whirlwind introduction into block codes. And next, we're going to look at how we can actually decode a block code. So see you in the next video.